In order to explain the emission spectra of elements, we will find that we need to invoke the idea of states. An atom is in a given state, and there is an energy associated with that state. This leads to the idea that the energy of atoms is quantized, rather than a continuous range of energies at which an atom can exist. Only certain specific energies are allowed, which correspond to different states. Let's look at a graphical display of this idea and introduce some of the language associated with absorption and emission. We can make a one-dimensional plot of energy on the y-axis. The state that atoms normally reside in is called the ground state. This is the lowest energy level on our plot, consistent with the idea that systems in nature seek the lowest energy they can find. In the demonstration, in order to produce light from the discharge tubes, we had to input energy. When the atoms absorb energy, their energy increases. As a result of this absorption, they can enter a higher energy state called an excited state. As we know, systems in nature prefer to be in lower energy states. In order to get back down to the ground state, the atoms have to get rid of some energy. One way to do this is to emit a photon, which results in the light that we see. The reason that this experiment is so important is that the energy of the photons that are emitted give us an experimental measure of the energy difference, which is given by the symbol delta E, between the states. This is sort of like watching someone at an ATM. If you see the machine give that person $20, you don't know what's left in their account, but you do know there's a $20 difference before and after the transition. It's important to understand that with atoms, the energy levels are fixed. If they were allowed to move around randomly, well, some atoms would have a small energy difference, others would have a medium energy difference, still others have larger energy difference. Although one atom puts out one photon, if you had all possible levels available, we would see white light with all wavelengths present. But we don't. Now, there is more than one color because atoms have more than one excited state available. But there must be fixed energy levels. We only have certain colors. Much like the ATM, the energy that of the photon tells us the energy difference before and after the transition. The energy of an atom must be quantized, not continuous.